Hello, Dr. Ramani. My name is Yusuf Al Bayati.
And my name is Talal Khalid, and today
We're representing our project about the electrical design for multi-story building. The main purpose today is to unveil the miscellaneous planning and calculations behind the electrical design for our multi-story building. Our aim is to showcase how our design ensures safety, efficiency, and compliance with the regulations. This presentation outlines our approaches and findings in the design and the electrical systems. Our objectives for this project is to design an electrical circuit for various applications, determine the appropriate breaking sizes, cable sizes, and contribution board layouts, and to estimate voltage drops to ensure compliance with safety standards and ensure reliable power distribution across all floors.
okay, let's describe the breakdown of the design process. How did we design this? And the overview of the tasks undertaken. So first, we do the circuit design for lighting, sockets, heaters, and etc. Uh, Breakers, cable sizing, and calculations. Distributions, board layouts, and the volt and estimating the voltage drop.
For our task breakdowns, we have the lighting and fan circuits, and the design layout and sizing calculations.
We also have the pipe size, wire size, MCB ratings. We also have the twin switch socket outlet circuits.
And the layout design and circuit configurations, and socket outlets locations, and wiring details.
Water heaters, washing machine circuits. We also have the breakdown of the design considerations and the MCB ratings.
And the pipe layouts and the wiring configurations, and the cookers, and the air conditioning circuits.
We also have the circuit design and the MCB selections. Finally, the pipe layout and the wiring diagram.
In result, here we can find the design of the light and the fan circuit. We can see that it's perfectly distributed among the floor, extending from the dining hall to the kitchen and all the way to the balcony and to the bathrooms and to our master bedroom and to our other bathroom and bedroom. And the design of the twin socket outlet circuits, we can clearly see that we have one in the bedroom, and we have one for the dining hall, and we have one for the kitchen, and we have one for the balcony, and we have another one in the master bedroom. In fact, we have two twin switch sockets in each bedroom. The design of water heater and washing machine circuits. We can find the design. It clearly shows that we have a water heater in bathroom 2 and bathroom 1. Okay. And for the washing machines, we have a great simulation here for where it's supposed to be in the floor.
It's near the balcony, it will be. Let's go for the design of cooker and air conditioner circuits. In this first diagram, we can see that the cooker is, there's two cookers in the kitchen only, and it's all connected to the breaker.
And for the air conditioner circuit, we have a master air condition in the dining hall, which covers the whole dining hall. And we have an air conditioner in the master bedroom, which is also connected to the bathroom and to the other bedroom. And the current per phase calculations of a single flat, we can find them in the below listed
table. We have the branch circuits from number 1 to number 12. Okay. We also have for each circuits the loads. You can see light fans, power socket, water heater, washing machine, cooker, and air conditioner. And the quantity, how much in each flat. Also, in the line current, there are three phases. We have phase 1, phase 2, and phase 3. Okay, each one we have to calculate, and we have to get the current per phase, the total of them.
And at the end, we can see the current per phase for each phase is approximately the same among all three phases.
So let's go for the total kW and the kVA of a single flat. Okay, we have the same from circuit branch from number 1 to number 12. And the rating, the cable size, and the load as the table shown before, and the quantity. And also we have the watt per load, each load, and how much it's the power of it. There are also three phases for this one. There's phase 1, phase 2, and phase 3. So we can see here in the table, okay, that for phase 1, not all loads can go for phase 1 or phase 2 or phase 3. So each load have its specific phase. And let's go for the single line diagram of a single flat. Okay, here, okay, we have this diagram, the single phase disconnect switch, okay, to the motor. This is the diagram for each circuit diagram,
which includes the light and fan. We have two of those, and we have three sockets, and we have two water heaters and a washing machine and two cookers and two air conditioners.
Okay, let's go for the SDB to flat connection. It's the same for each floor. Okay, here in the first floor plan, we can see that how it's connected to each other in each floor. Let's go how to show the three-phase energy meters to three-phase isolator to each flat. Okay, so we have the three-phase incoming supply. It goes to 4 isolators. There are 4 isolators because we have 4 flats. And each flat will go to the energy meter. From the energy meter, it will go to each flat. Let's go for the incoming line current at each floor.
For the first floor and the second floor and the third floor, we can find the end result is approximately the same, which is 94.4 ampere. Okay, and that shows that, just like we mentioned at the top, our main purpose is showing that the calculations are almost the same, and ensuring reliable power distribution across all floors. Okay, and after that we have the total line current and cable selection with cable path. So the total line current for the above cable, 94.4 times 3 equals 283.2 ampere. Type and size of the cable is 120 millimeters squared TPN and a 70 millimeters squared E. The type is the NYY.
So let's say for the main type, for the main distribution board, okay, we have the three-phase cable, okay, going to the duct, okay. Then the duct goes to each floor, the SDB for each floor, floor 1, floor 2, floor 3. These phase incoming supply goes to each flat through the isolator as the previous diagram. So let's go to the pipe selection for the building. First, we have to calculate the pipe hydraulic. we calculated and we saw that it's 561.63 watts. Okay, we considered that the motor efficiency is around 90%, so it's 0.9. So the power motor, it's calculated as below, which will be 600, approximately 624 watts.
The motor power ratings are standardized. Therefore, select a motor with a slightly higher standing rating to ensure reliability and accommodate any unforeseen loads. The transformer rating selections. The transformer kVA rating. Motor power 0.75 kilowatt. Other powers 16.61 kilowatt times 4 times 3, which equals to 199.32 kilowatt. So the total power is 200.07 kilowatt.
So let's calculate the minimum kVA rating of the transformer. So let's say that the power factor is 0.8. Okay, so we take the power, the total power, and we divide it by the power factor. We will get 250.08 kVA. So any transformer which is rated higher than this kVA can be installed. For example, 290 kVA, 300 kVA can be installed. So let's go for the voltage drop calculations, which is the last task. The voltage drop from the MDB to any one of the FDB at the third floor is approximately 0.85 volts. And for the three-phase pump motor, is approximately 0.232 volts.
And thank you for listening to us. And if you have any questions regarding our project
You
or
can email us.
presentation, you could
Email
contact us through the email.
Thank you so much for listening to us. And this was our presentation for the design of our floor plan.
Thank you, sir.